So now we're going to learn function notation. So let's name the functions that relate the dog's distance from the post to the time since the owner left. The function is going to be named F for day 1, G for day 2, and H for day 3. So the input of each function is the time, and the output is going to be the distance. So I'm going to start with this one. So the distance from the post, 60 seconds after the dog left on day 1. Now, we're going to call this function f. So this right here is just called the name of the function. So I'm putting the name. And then I put f of, and then we have 60 seconds. I'm putting f of 60. Again, this number is our input, or what the x variable is. And then we put is equal to, and then we put our output, which was 4 feet. So if you remember, I'm just looking at this. We say our input was 60 seconds, our output was 4 feet, and we call this function f. So we say f of 60 is 4. So for day 2, we call this a new function. So remember, for day 2, the function is called g. So we say g of 60 seconds. And again, if I'm looking at my data, that was 4 feet. So we say that equals 4. So again, to get a handle of this, g is just the name of the function. The 60 is your input. And then over here, I put that was feet, that was my units, but this should really just say this is the output number of the function. So let's fix that. So day 3, our input is h of 60 is equal to 4. Again, h is just the name of the function. The 60 is your input. The 4 is your output. So the distance from the post when the owner left, well, that's at 0 seconds. So we have that data here. So our input is going to be 0 for all the functions, and our output is going to be 1.5. So again, we say f, the name of the function at day 1, of 0. Our input is 0 seconds, equals, and it was 1.5 feet. So this smaller notation is just saying on day 1, at 0 seconds, the dog was at 1.5 feet. Really concise way of writing this. That's why mathematicians use it. So on day 2, the function is g. So g of 0 was 1.5. Again, you can just flip back to the other page, or I have this data right here written down. So this is f, g, and we're going to say h. So h of 0 was 1.5 as well. Again, we have the name of the function, the input, and the output. So here, the distance from the post, 150 seconds after the dog left. So we would put here f of 150 equals, and going back to the picture, I have to go and look at 150 because we had 160 on there. So here, 150 looks like it is at about 3. We'll say 8. So then g of 150 seconds on day 2. We'll go back and look at that graph. So here, 150 seconds is about there. So on day 2, the dog is at 4 feet. So to write that in this notation, g of 150 is 4. That means on day 2, after 150 seconds, the dog is at 4 feet. So now we do the same thing with h. So h of 150 equals, and we just look up what is the input and what is the output. So we have 150 equals, and then that would be about 0.5. So now we have to describe what each expression represents. So if we did f of 15, this would be on day 1, after 15 seconds, the distance of the dog. So we can write that a little bit differently and just say the distance on day 1 after 15 seconds. And then g of 48, so this is day 2. So we can say the day 2 distance after 48 seconds. And then h of t, this would be the day 3 distance after time t. So here the equation g of 120 equals 4 can be interpreted to mean on day 2, 120 seconds after the dog owner left, the dog was 4 feet from the post. What does each equation mean? So again, if we look at h of 40 equals 4.6. So if we look at function h, that's on day 3. So on day 3, this would be after 40 seconds because that's our input. The dog is 4.6 feet from the post. And I'm not going to fit all of that in. So F is day 1. And then at time t, the dog is 5 feet from the post. And then this would be function g, which is day 2. So on day 2, at time t, the dog is d feet from the post. So if you notice, function notation is very handy because we have a large sentence and words here, which is written in very small mathematical notation.